is the uh, this is a statement from a famous computer scientist who worked in IBM during 1960s. His name is Rolf Landauer. He said, ultimately, information is physical. And other aspect of information is that information is connected to entropy. There is another fundamental concept in nature. The amount of, you must have studied about Shannon's theory of information in your classes, right? So again, another concept. This concept of entropy is very fundamental. In fact, how many of us know the word entropy is not from English? Entropy is a Greek word which was used initially in German language, and later on it was used in the originally in a paper, research paper published by Boltzmann, a famous physicist who worked in early 1900s. So coming back to the fundamental concept of quantum computing, this starts with our exploration for making energy efficient machines. Now we are getting into an era when the conventional computing, as we know, we call it classical computing, it has reached a roadblock. The moment you are getting into nanometer level semiconductor manufacturing, it is no longer giving you result as per the Moore's law. We have been following Moore's law as a very sacrosanct law in the world of computers. Moore's law has been proposed by Gordon Moore, who is one of the inventors of transistors, who worked in Intel, right, who co-founded Intel, right. Moore's law has been challenged because of the thermodynamic limits. That is precisely the reason why the world is looking at a solution. And the world over, quantum computers are looked at as the potential solution where you can solve the energy efficiency challenges of conventional classical computers. But there are more reasons beyond just energy efficient computers. Some problems which are conventionally difficult for classical computers, like traveling salesman problem or graph isomorphism problem, these kind of problems cannot be solved using classical computers efficiently. Even for these problems, quantum computers are considered to be a solution. All of this started way back in, just like we mentioned, this journey started in early 1960s. So when I'm talking about the origins, there is a particular person whose name is forgotten in the history of computing. His name is Konrad Zuse. I'm not sure how many of you have heard this name. Konrad Zuse is the person who invented Z series of computers. Is there anyone who knows this name, Konrad Zuse? He was a German, and he was working with the Nazi government, and his computers were so precise that they were used in the warfare. And then his series of computers, Z1, Z2, Z3, these series of computers were used in for missiles and other telecommunication purposes. So Konrad Zuse wrote a book in 1960 called Calculating Space. In this book, he precisely explains how quantum mechanical phenomena could be harnessed in computation. And along after, during this period, there were a lot of discussions on the viability of using quantum mechanical phenomena for processing information. And thereafter, a few scientists from US, like Toffoli, Toffoli is a scientist from Italy who migrated to US, and there is another scientist, computer scientist known as Edward Fredkin. They used the theories of Conrad's use, and they came up with a theory known as conservative logic, a new kind of logical system where energy is conserved while you are processing information. Because energy dissipation was a big challenge for computers in those days. And now we are witnessing the same challenge. So many years afterwards, when we are reaching the Moore's law's limit, thermodynamic limit, we are again looking at the fundamental paradigm called quantum computing with more rigor. Right now we know that we have created so many quantum computers. When I started hearing about quantum computers in early 2010, it was only one company known as D-Wave. D-Wave was working on a process known as quantum annealing, using a adiabatic model of quantum computation. They created new kind of quantum computers which were working on were good for optimization problems. Optimization problems could be for supply chain, could be for different planning problems, linear programming related planning problems. They came up with a quantum computer known as adiabatic quantum computer. I was really excited. And in the same time, almost in the early 2010-11, IBM came up with another approach for quantum computer known as superconducting quantum computer. But before all this, in the early 2000, MIT created very small version of quantum computers. We call the unit of quantum computing by the term qubit. So they used a concept known as nuclear magnetic resonance. So we should remember that nuclear magnetic resonance is the first form of quantum computers. Thereafter, they couldn't scale it up because of the noise produced by quantum computers. Thereafter, D-Wave came up with adiabatic quantum computers, and thereafter IBM came up with superconducting approach to quantum computing. And thereafter, we are seeing a surge in quantum computing in perhaps after 2015. A new company known as Rigetti, they came up with another quantum computer, again using superconducting quantum computer approach. Afterwards, another approach came in. Intel and University of Sydney created quantum computers using photonic quantum computing approach. So we will talk more about all these approaches today. Let's begin the session. First, I would like to explain why do we need quantum computers? What are the kind of use cases, problems we can address with quantum computers? Let's go to first slide. Next slide, please. First and foremost, quantum computing is about simulation. This is what Richard Feynman proposed in 1984. He proposed the idea of universal quantum simulator. If you look at the history of computing, computers were actually in the early days, they were created for simulation purpose. Simulating a physical process. This was the initial thought process behind computation. What do we understand by the term simulation? Simulation means it's about identifying similarities and differences from an abstract reality. So here we are talking about simulating quantum mechanical phenomena. For example, something related to new photosynthesis. Even today, photosynthesis remains ununderstood. No, it's a mystery for humanity. How we are the fundamental processes, the quantum biological processes underneath photosynthesis is still unknown. For understanding how we produce nutrients in photosynthesis, we could use quantum computers. And the main reason why quantum computers are useful for simulating the quantum mechanical reality and the physical reality is the number of variables that we encounter in the natural processes are phenomenally big. So recently I came across an article which says about processes in nature are not always in equilibrium. There are a lot of processes which are in state of non-equilibrium. These kind of processes cannot be modeled using classical computers. Next slide, please. Then, very important problem nowadays is factoring large numbers. This is a problem of prime importance for anyone who is working on cybersecurity and cryptography. Right now, we know that one of the most widely used cryptographic scheme called RSA is based on the problem of factoring prime numbers. There are two sets of algorithms. One is discrete logarithm based and second one is based on the prime number factorization. So both of these problems are some way connected to factorization. So for solving these kind of problems, quantum computers are now being attempted. In fact, the first demonstration of the viability of quantum computers was done factoring a very small number known as 15. It was done in IBM way back in 1990, if I remember correctly. To find a factor of 15, 3 and 5, we know by our mental arithmetic how it is easy to find factors. But if you follow an algorithm, it is not an easy to find an algorithm to find factors. This has been solved using a specific algorithm, quantum algorithm known as Shor's algorithm, named after a computer scientist named as Peter Shor. So the potential of Shor's algorithm is phenomenal. If you are able to break RSA, it is going to break a lot of cryptographic schemes implemented across the world. And not only that, right now, one of the original contributors of Bitcoin protocol, Adam Back, he has said, quantum computers will help to create better cryptographic schemes because that will help you to test the formidability of the existing algorithms. Right now, a new stream of cryptography known as lattice cryptography is becoming popular thanks to quantum computers. Because this lattice cryptography has been considered as quantum safe. This is a scheme of algorithm which cannot be broken easily by quantum computers because they use a different arrangement of numbers in a particular infinite array of vectors, infinite vector arrangement called lattices. So factoring large numbers. So the best known classical algorithms, when they try to break the RSA, they grow in exponential size. This is the reason, second reason why quantum computers are in demand. Next slide. Yeah, this is the detailed explanation of exponential speedup in Shor's algorithm. So any integer can be factored using Shor algorithm in roughly n square times, whereas classical algorithm will take 2 raised to n in exponential times. That is why Shor's algorithm is considered to be better than classical algorithm for solving prime number factorization problem. Next slide. Another important area where quantum computers are being used or proposed to be used is Grover's algorithm. This is created by another computer scientist known as Love Grover. This is related to sorting an unordered database. Let's say a telephone directory. When you want to find a particular number from a telephone directory, similar problems like call data, analyzing call data records, right? For all these kind of problems, the classical algorithms take exponential time. But here in Grover's algorithm, it achieves this in a quadratic time complexity. Though it is not giving exponential speed up, it is still a significant improvement. This has been used now for image search related problems in Google. They are using Grover's algorithm internally for solving image search related problems. At the moment, they are doing research on it. Next slide. Yeah, the another problem is related to optimization problem. One example is problems which can be modeled as traveling salesman problem. It's related to finding the shortest route that visits a set of cities. For these kind of portfolio optimization problem, the quantum computers, especially there is a set of algorithm known as quantum, it's called, it is a hybrid algorithm. Combination of classical and quantum algorithms could be used for solving optimization problem. It's known as QoA problem algorithm. This algorithm is very effective for solving optimization problems. Next slide. Machine learning is the other area where so many quantum algorithms have come up. One direct, very popular example is quantum support vector machines. All of us have heard of support vector machines, which is a very good algorithm for classification and regression problems. So for creating kernels in support vector machines, we can create quantum kernels using quantum machine learning approach. There is a company known as Penny Lane, which is exclusively working on quantum machine learning problems. They are also working on creating quantum neural networks and different other variants of quantum machine learning. But quantum support vector machines are considered to be the most popular among different quantum computing approaches. Neural network approach, the backpropagation cannot be easily implemented using quantum computers. The feed-forward neural networks can be implemented, but backpropagation has some challenges when you are trying to implement in quantum mechanical way. Next slide. So I hope this slide is visible. This slide talks about different use cases of quantum computers, ranging from life sciences, chemical, energy, telecom, manufacturing, logistics, and finance. Let me try to mention some of the problems. One, molecular simulation. As we mentioned, in life science, simulating the behavior of in the drug design, molecular simulations, quantum computers are considered to be very powerful tool. And then for protein synthesis is another area. And then another area in energy is carbon capture related new material design. And in telecom, designing new semiconductor materials. There are plethora of use cases. What I will do is I'm anyway sharing this presentation with you. You can go through these use cases. In a nutshell, quantum computers have applications in domains like financial markets, um, in machine learning, simulation, and optimization problems. Let's move forward. So now I would like to show you a single slide on how a quantum computer works. Next slide. The quantum computers cannot work in isolation. Quantum computers need access to the classical data. So it begins with feeding classical data as an input. You have to encode the classical data into a format known as quantum bit format, qubit format, using certain kind of matrices. We will understand about different kind of matrix terms we use in quantum computers shortly. So we have to understand the classical data has to be ported into the quantum circuits. There are a lot of engineering nuances involved, like we use different kind of the input processing lines and methods for getting the classical data. But we have to understand, we encode the data, then we initialize the quantum circuits. The quantum computers use combination of circuits and gates. In classical, our conventional computers, we know we have a lot of circuits, right? Logical circuits. In cryptography, we use arithmetic circuits. Likewise, in quantum computing world, we have quantum circuits. And quantum circuits are created using quantum gates, combination of different quantum gates. So this circuit has to be initialized. Initial state is very important for executing set of quantum algorithms. There are a set of quantum algorithms related to every quantum phenomena. We will understand more about quantum phenomena. For example, in quantum mechanical world, we have probabilities. We deal with more than certainties, we deal with probabilities. We measure probabilities. The quantum state is measured as probability. When we measure it, it has amplitude and phase. So all this measurement is important. When we measure from a quantum circuit, we get probability distribution. And then we have to apply error correction. This is a major task for quantum computers, because in the quantum world, we are not working in the ideal quantum computers. We are working with noisy intermediary state quantum computers. We call them NISQ. So these computers produce noises. And to correct this error caused by these noises, we use error correcting methods. You must be studying different error correcting methods by now, right? Different encoding approaches, different error correction schemes. So likewise, in quantum world, there are set of error correction algorithms used. And the major challenge is decoherence. The quantum state wither away. So due to the noise, when the quantum state, when a particular circuit is in quantum state, we say it is in a coherent state. The moment it wither away, we say it is decoherent. So we will get into that. So essentially what we say, there are two major quantum mechanical phenomena, superposition and entanglement. So both these phenomena are important for the functioning of a quantum computer. In a decoherent state, we will not be having entanglement. And this is a problem we address through error correction. Recently, Google introduced a chip known as Google Willow. It had created a lot of news, right? That was a major achievement in terms of error correction. In error correction, they made a lot of progress with this Google Willow chip. And so, yeah, after initializing the quantum circuit, I missed a point. We apply quantum gates, we apply error correction, then we measure, and after that we decode, then we get the output. So this is the flow of a quantum computer, from input to the internal process to output. I hope this is clear. If there are any questions, you can ask now. let's proceed. We can have questions at the end. Next slide, please. So I would like to take a quick glance at the history of quantum computing. Everything began with the Planck's hypothesis in 1900, but even before that, there were contributions on entropy by Boltzmann. 1935, the EPR, Einstein-Podolsky-Rosen paradox related to entanglement was presented. Then Bell's inequality related to entanglement was another major theoretical foundation. So in early 1970s, the foundations of quantum information theory has been laid out by different people like Charles Bennett in US and Yuri Manin in Soviet and Komogorov. All of them contributed to quantum information theory. 1980s conference has been a major milestone. This is where Richard Feynman presented the paper on universal quantum simulation, where he presented why quantum computers are essential for modeling quantum mechanical processes, why classical computers cannot be used. And then he came up with the proposal, and thereafter in 1982 itself, topological quantum computer model was proposed, which has been taken up by Microsoft in the recent times, but there has been, it is not yet proved to be as efficient as the superconducting approach. And thereafter, Paul Benioff came up with a quantum Turing machine model. This was a major milestone. The quantum Turing machine, the classical Alan Turing's machine, Turing computational machine model was not sufficient for physical processes, because in the Alan Turing's model, it was not modeled for reversible processes. So Paul Benioff in his model came up with a quantum Turing machine model, and this was endorsed by a British computer scientist, David Deutsch. David Deutsch formalized this paper, Paul Benioff's paper, into a very famous paper on quantum Turing machine. And then the people like Charles Bennett and others have worked on quantum key distribution. We have to understand quantum cryptography and quantum computing are different. Quantum cryptography is using quantum mechanical phenomena for secure transmission of information. It could be using photons, or it could be using any other physical mechanism like spin, photon. But quantum computers are modeling or simulating natural processes using quantum mechanical state machines. And thereafter, David Deutsch in 1985 came up with the paper called Universal Quantum Computer, and the big breakthrough came up in 1984 when Peter Shor came up with the algorithm which can break RSA. That was an eye-opener for the world. Prior to it, everyone considered it to be a scientific computing approach. But Peter Shor, when he shown to the world that using a concept known as quantum oracle, if you can break the conventional cryptographic schemes, this is going to be very significant. World over, nation states, banks, everyone start looking at quantum computers. But that was too early, even though Peter Shor and IBM demonstrated on a very small level, factoring 15, then large-scale experiment had to wait, because nuclear magnetic resonance was not able to create pure qubits. And same year, Love Grover came up with the Grover's algorithm, which will help to sort unordered databases. And thereafter, Divin Shiro came up with the criteria for quantum computers, a set of criteria that we will go through in later part of the session. And then first ion trap quantum computer was created in 2000. This is an alternating model for quantum computers, alternate to superconducting model. Our IIT Kharagpur and lot of other startups and big companies are working on building ion trap based quantum computers. And then Transmon quantum computer superconducting qubit was demonstrated in 2007. We will see different kind of superconducting approaches in a couple of slides. 2013, Rigetti came up. 2016, Microsoft came up with topological quantum computing approach. Google rose to prominence with their superconducting approach in 2019. And thereafter, we are seeing a plethora of companies getting into this space. Next slide. So this is the ecosystem right now. Big companies like Merck, Airbus, and JP Morgan, Wells Fargo, Goldman Sachs, and health insurance, AstraZeneca, Volkswagen. A lot of companies are already invested heavily into quantum computing space. A lot of startups are there, and leading companies like IBM, AWS, Microsoft, Honeywell, and startups like Rigetti, Cambridge Quantum, they're all into this space. Next slide. So this is another look at the history. The 2-qubit quantum computer demonstrated in 1998 by IBM and MIT. Then in Germany, TU Munich demonstrated 5-qubit quantum computer. And thereafter, Los Alamos National Laboratory, they are pioneering quantum computers quite a lot even nowadays. They came up with 7-qubit quantum computer. MIT continued to produce 2000. They launched a venture known as Institute of Quantum Computing. Now, can we move to the next slide? So this is the current map of the quantum computing space, how it is moving on. In fact, in 2029, it is IBM and Google are championing with their quantum computing roadmap. They are both attempting to in two directions. IBM is trying to do quantum computers which can attack the RSA more significantly with 1000-qubit quantum computer, whereas Google is moving towards applying quantum computers for machine learning more seriously for problems like image search and optimization problems likewise. So other companies are again pretty much active in this space. Next slide. So these are the most popular approaches for building quantum computers: superconducting approach, ion trapped ion approach, spin-based approach, topological approach, photonic approach, and neutral atom approach. We will see the details in the next slides. Now let me take a few minutes to explain the fundamental concepts. So first thing we have to understand is about superposition and entanglement. We will go through these concepts, and then once the qubits are different from classical bits because of their ability to exist in a phenomenon known as superposition. They give some more possibilities than classical computers, and entanglement gives stability and correlation to the quantum mechanical states. We will get into those details, and then we have to construct quantum gates that perform operations on qubits. When we measure, the quantum states collapse and we get the probability measurements. And then the quantum algorithms are set of algorithms which like the phase estimation algorithm, amplitude estimation, oracle algorithm. There are set of algorithms, even algorithms named after Peter Shor and Grover and David Deutsch. There are a lot of algorithms. These algorithms are harnessing the quantum mechanical states and phenomena. And then quantum interference is another concept which is a very interesting concept which was demonstrated in the double slit experiment. So it is even so there are two kinds of interference: constructive interference and destructive interference. Constructive interference can be used for amplifying the probabilities, whereas destructive interference can be used for eliminating the probability. of occurrence of a particular event. So this interference can itself be used for our specific needs in a quantum computer. Now, let us understand about superposition. In classical bits, our classical Boolean logic, the bits can exist only on 0 and 1. Whereas in quantum bits, they can exist in both the states simultaneously. So this means it is a combination of both 0 and 1. It can be written as a combination of linear combination of alpha 0 and beta 1, where alpha and beta are complex numbers. 0 and 1 are known as column vectors. So this representation is known as Ket notation. This has been invented by a physicist known as Paul Dirac, and this notation explains this actually is a concept from linear algebra, which is very important when we study about quantum computers. So this means that when a particular quantum bit is in existence, it can be measured in the combination of the two complex numbers alpha and beta, along with the two vectors representing 0 state and 1 state. So this helps us to create a computational state machines where multiple possibilities can be computed simultaneously. So this can be constructed, this kind of qubits can be constructed using photons, atoms, spins, etc. Next slide. So this is how we represent qubits. On the left side, we are seeing normal bits, which is either on 0 or 1, whereas qubits are in the combination where we see both 0 and 1 as the vectors and alpha and beta as the coefficients, the complex number coefficients. Next slide. Entanglement is a little bit more counterintuitive concept. Entanglement means the qubits will be linked they have a shared state even though they are physically separated. So when you measure a qubit in entanglement with other qubit, so when you measure the state of one entanglement qubit, it determines the state of other. It helps us to create advanced correlations and dependencies between qubits, and it has been used in a lot of algorithms, quantum algorithms, extensively. So for example, when you want to create product states, quantum entanglement is immensely useful. When you want to do operations like vector multiplication, we create tensor states. This again, entanglement is a very powerful operation, useful in this context. Next slide. So to depict this pictorially, quantum states exist in superposition. When you measure, it collapses to the individual probability, and then we can do parallel arithmetic operations through superposition, and then we can do exponential multiplication operations, and maximum amount of data can be transmitted using entanglement. Next slide. And another fundamental concept we have to understand is quantum gates. Quantum gates are the building blocks which operate on qubits. They create operations, they operate on superposition, and they create entanglement. And we represent them using a concept known as unitary metrics. We have a slide on explaining what is a unitary matrix. So this unitary matrix is a mathematical model which explains that quantum operations are reversible. This is one of the fundamental requirement. When you look at quantum mechanical computation, it has to be reversible. So the quantum gates, there are different examples of quantum gates. One popular quantum gate which is used for superposition is known as Hadamard gate. Then for different phase inversion operations, we use Pauli gates, X, Y, Z, into different axes. And for other kind of controlled universal operations, we will explain about them. There is a set of gate known as controlled NOT gate. This controlled NOT gate helps us to construct universal quantum computers. We know that NAND gates in classical computing are universal gates, right? So similarly, CNOT gate and its higher variants can be used for constructing universal quantum computers. So this shows the representation of different quantum gates. The Pauli gate is represented with Pauli X, Y, Z gates are represented with X and Y and Z. Hadamard gate is represented with H, and this Hadamard gate is used for superposition, and we will understand why it is having 1 by root 2 with 1. This is the matrix representation of Hadamard gate, and control NOT gate is represented below, which is nothing but there are two specific lines in this. The one is the target gate, one is the target bit and the control bit. So the control bit and the target bit are controlled, represented by the CNOT gate. Next slide. Yeah, this is about measurement. We can move forward. Yeah, next slide. Next slide. Next slide. So let me get into the engineering aspects of quantum computers. We have seen this slide in summary in the previous one of the slide. Superconducting qubits, semiconductor quantum dot, trapped ion photonic approach, then defect-based qubits, topological qubits, and nuclear magnetic resonance-based approach. These are the different approaches to building quantum computers. Next slide. So first let us see how the superconducting quantum computers can be constructed. So here one of the approach is essentially it is all about creating a two-level system. There we have a particular concept known as transmon qubit. There are different kind of superconducting. I hope all of you are familiar with superconducting materials, right? The materials which has zero electrical resistance. So superconducting materials are used to create quantum mechanical phenomena, and they are controlled using magnetic flux. It's a can you go to next slide? So one of the first approaches known as using transmon qubits. So they are based on a non-linear oscillators, and they keep the quantum state for a longer time compared to other approaches. That's why transmon qubit based quantum computers, superconducting quantum computers, are used more prominently than others. Next slide. There is another approach called X-mount qubit. It is again a variation of transmon approach with a different approach to qubit connectivity, because we use multiple qubit in a quantum computer. Next slide. Flux qubit is the other approach. They use something known as Josephson junction in superconducting quantum computers, and this also creates something known as Cooper pair of electrons. And this Josephson junctions are used in flux qubits, and they have strong interaction than conventional other qubits, which will be useful for certain quantum operations where the qubit-to-qubit interaction is more required. Next slide. This shows the trapped ion quantum computer where ionized atoms are trapped inside magnetic field. This is again a two-level system. Next slide. There are different approaches. One is known as hyperfine approach. So here multiple atoms are used and qubits are encoded in multiple energy levels of atoms. Next slide. The second approach is using optical qubits. Optical qubits are essentially using lasers. Lasers are used to increase the energy level in atoms by exciting them into ionic state. Next slide. Then another approach is known as neutral atom quantum computing. Here again we are using trapped ions, but they are trapped in optical lattices. So they use optoelectronic approaches. And it is furthermore cooler. So there are different kind of engineering techniques are used here, like optical trap, magnetic trap, and they are again mapped into different energy levels of individual atoms. Here again, lasers are used for manipulation of qubits. Next slide. This is a not very popular approach, but this has been considered as another approach for quantum computer construction, where quantum dots are used. Again, the quantum dots are constructed and they are controlled with microwaves, and it creates a two-level system where there is a electron spin or charge. Next slide. So it's a kind of nanocrystal. Quantum dots are semiconductor nanocrystals. They can trap individual electrons or other charge carriers. So again, the electrons which are trapped inside the dots are represented by their spin. So these qubits are manipulated by microwave pulses in this approach. Next slide. Optical quantum computer is the other approach where photonic quantum computers are constructed. This is really engineering approach wise very advanced to construct. Intel is working on optical quantum computers. Even University of Sydney is working on this approach. Photonic approach. They use polarization state of the photon or the frequency of the phases. And the superposition and entanglement are created using waveguides, wave plates, whereas qubit manipulation is done using beam splitters. Next slide. So let me show you a quantum hardware, how a quantum computer hardware is built in a superconducting quantum computer. Different quantum computers have different approach to hardware. I'll show you how the superconducting quantum computers hardware is constructed. Next slide. These are the hardware. This is the photo of a superconducting quantum computer. So this uses a specific kind of a refrigerator. It has the source is microwave source which generate the initial signal at room temperature, and then different transmission lines are used to carry signal in different temperature level, and then there is a thermal state where signals are attenuated to prevent signals are they control the temperature to 10 Kelvin to prevent the material loss. Then there is a mixing chamber. If you see here, you can see that the temperature comes down drastically the moment you reach the qubit chip. Next slide. Yeah, these are the other components. For measuring qubits, we again use attenuated microwave signals. Then there are readout lines, and then there are low noise amplifiers which are used for final measurement. Next slide. This diagram shows the components in much more detail. From the room temperature, we have microwave source, and then there are low density metal interconnect that connects the controllers. There is something known as specific kind of flux qubit approach is mentioned here. There are control computers and memory hierarchy initially, and then the superconducting control wires, specific kind of wires are used. You can see the temperature level. The moment you reach the chip, it reaches millikelvin temperature. So for cooling, as you see on the left side, you can see gold-plated copper cooling is used, and temperature. You can see that different kind of cables are used here, coaxial cables, and finally the quantum chip is at the bottom, as you see here, which is at 10 millikelvin. Next slide, please. So I've spoken about this, but let me quickly go through the early history. It is all about reversible computing. We initially thought the computers are not reversible, whereas natural laws are reversible. Next slide. So this is Lander, who said, information is ultimately physical. So every reading of information is a dissipative process. This is what Lander has observed. Next slide. So when you look at even older computers like Intel Pentium, sometimes like 100,000 bits per flop will be discarded, even in a readout operation, even if you take the minimum loss model. So this is the loss level in a classical computer. Next slide, please. So reversible, traditional computers, even by the design, are not reversible, because even if you look at AND gate, we pass 2 input and take 1 output. That model itself is not reversible model. This is the challenge, why people have thought about need for reversible computing. Next slide. Yeah, so I think this history we have spoken now. We'll quickly move through the history. In 1961, in IBM, they started working on reversible computing. Initially, the Fredkin gate and Toffoli gate were proposed in 1970s and 80s. Next slide. And next slide, please. So in 1973, Charles Bennett made a remarkable discovery. This is very important. He has identified that classical computing can be broken down into steps. So the multiple steps, if you take a different route, you will be able to come up with a different set of gates. Right now we talk about C-node gates, right? I just mentioned about C-node, control node gate. If you take such an approach, we can avoid losing information, even in classical systems. Next slide. So his approach, Charles Bennett approach, is that we can arrange classical computer to compute reversibly very slowly with an energy as small as we need. And then based on this, Richard Feynman came up with a model of reversible computer which moves forward and drifts back. This is the approach Richard Feynman proposed. And we just mentioned about the limitations of classical gates. Even if you use NAND gate, the universal classical gates have a limitation, because from output it's not easy for you to detect the input. That is why classical approach was not used in reversible computing. Next slide. Yeah, the key inference is, for reversibility, we need to carry information to additional rounds. Next slide. And I think we can skip this section. Can we go to next section? These are the profiles. You can go through them later. Rolf Lander, Charles Bennett, Toffoli, Fredkin, their concept of conservative logic, and then came, next slide, Yuri Manin and Paul Benioff, Richard Feynman, David Deutsch. Now let us go into some details of the theoretic foundations of superposition. So superposition means you can do multiple computations in parallel by processing all possible states of qubit at once. This is the parallelism, but it is valid only till you measure it. The moment you measure it, it collapses into one of the basis states. We have to understand what is a basis state. This is a concept we use in vectors in linear algebra called basis vectors. So the unit vectors we mentioned 0 and 1, right? They are nothing but basis vectors. Next slide. Entanglement is much more sophisticated concept. It's a completely non-classical phenomena. It's related to shared quantum state, where between two or more systems, even if they are separated by large distance, they will share a quantum memory. The people even like Albert Einstein could not agree with the concept of entanglement. He mentioned that it is like spooky action at a distance. But it has been a cornerstone of quantum computing. So the implication is that when you measure one state of an entangled qubit, instantaneously determine the state of other. Next slide. So this helps in complex correlation. It helps us to get multiple qubits to work together, like dancing with qubits. That is a term used by a famous quantum computing scientist recently. You create a new kind of world, exotic world, where you can make multiple quantum bits work in harmony. So we can create complex correlations, and that enhances computational power. I have recently read an article which says entanglement is going to be the new source of power for this generation. If you are able, I'll share that document with you. It's published in Nature magazine. Next slide. So entanglement is technically related to the concept of wave functions. So it is related to the concept in such a way that when two or more systems are entangled, their wave function cannot be expressed as a product of individual functions. So you can't, essentially when you take a product of two vectors, and so when you create a product, right, you will be able to separate them. But in a quantum entanglement state, you will not be able to express them as a product. That is the unique thing about quantum entanglement. So entangled systems are described by a single wave function. Wave function is a concept introduced by Erwin Schrödinger. If we have time, I will be able to show entanglement wave functions concept. Let me quickly go to next slide. So entanglement helps us to achieve parallelism. Next slide. So quite a lot of slides on entanglement. It is also used for error correction. It helps us to avoid noise to an extent. Next slide, please. Interference is a mechanism we mentioned briefly. We can create constructive interference and destructive interference. Next slide. Next slide, please. Next slide, please. So mathematical foundations, if I can quickly touch upon. Vectors are very important concept for you to understand in quantum computing. Every quantum state is represented as a vector in a vector space. We have to understand the concept of vector spaces. So normally we use the concept of, there are two kinds of vectors, column vectors and row vectors. For convenience in matrix multiplication, we use row vector format in quantum computing. So operations like addition, scalar multiplication, and finding the norm are easily done if you are using column vectors. Next slide. So vector space is a space which satisfies the norm of independence, where we are able to create linearly independent vectors. And there is a concept known as span. Span is another metric of a vector space. And so there are certain postulates related to vector space, which I don't have the time to explain. Next slide. So basis vector are the fundamental unit vectors using which we can express other vectors. So any other vectors. The concept of spanning means any vector in a vector space can be expressed as a combination of basis vectors. Next slide. Matrices, we know, matrices are used for quantum operations because quantum operations are about transformations in the vector space. Matrices are used for transformations in the vector space, and it is done by quantum operators. Next slide. I think this can be skipped. Unitary metrics is a concept which I mentioned earlier. They are actually, these matrices preserve the inner product. So there is a concept of inner product which is used in vector spaces. So inner products are generally represented using unitary matrices. Can we skip this slide? Inner product, inner product of two vectors give a scalar, and it is normally used to represent the amplitude, probability amplitude of a particular quantum state. Outer product is used normally for a concept known as density metrics. This is a slightly advanced concept. Next slide. Next slide. Next slide. I think we'll quickly go to the quantum definition. So a quantum computer is defined as a computer with a register or a set of registers, and in which it has a unitary matrix for operations and measurement to extract information. So we need to create registers, and we need unitary metrics for operations and measurement to extract information. Next slide. If you represent quantum computer in a mathematical model as a set, it has the quantum register can be represented by something known as Hilbert space. The concept of Hilbert space is very, very essential when we study about vector spaces. It is different from the conventional Euclidean space which we used in classical computing and classical logic. And next slide, previous slide. U represent the quantum algorithm, M represent the measurement. So using the combination of Hilbert space, an algorithm, and measurement, we can represent a quantum computer. And if I may take a few more minutes. Okay. So there are more slides. I will explain the outline. In the next section, there is deeper aspects of qubits and different kind of quantum gates. There are single qubit based quantum gates which we spoke briefly, like X, Y, Z, and Hadamard gate, and these are used in basic superposition. And then there are multi-qubit gates which can be used for swap operation and different kind of Fourier transforms, advanced operations. Then there is a section on quantum algorithms. Quantum algorithms, whichever we mentioned here, Peter Shor's algorithm and different other set of algorithms are mentioned in that section. And there is other section on quantum error correction and control. So I tried to cover as much as information I could. The flow, I am not sure how much it is effective, but I tried to cover the history and the contemporary, the current context. This is a very futuristic world, very much transformative and creating a new form of computing. The world over, even in India, National Quantum Mission is a great initiative. Across India, there are a lot of universities, startups, and corporations working on this space. I wish all of you, I request all of you to explore this space and come forward. I'll be happy to discuss with you on further. We can connect anytime on quantum computing. I am the major concepts I am also learning about further aspects of linear algebra and how quantum physics works in finer terms. Thank you so much. for this, giving this opportunity. It has been a great pleasure and privilege interacting with all of you. Thank you once again.
Thank you, sir, for those invaluable insights of quantum computing. Your focus on problems which could not be solved by using classical computation efficiently but can be precisely solved using quantum computing is highly appreciated. Thank you, sir. We would surely like to have more such interactions with you. Thank you. I request all the students to be seated for the next session. Attendance will be registered for the next session as well.
Last session, guys. Last session.